Hi everyone. Today I'd like to lecture on measures of variation. In order to do that, I want to start with Scripture. Psalms 119:89, "Forever, O Lord, thy word is settled in heaven." So that just reminds us that God's word is definite, it's settled, it's done. And there's just so much power in that. His word is settled in heaven. And I do have a quote from First Lady Barbara Bush. "At the end of your life, you will never regret not having passed one more test, not winning one more verdict, or not closing one more deal. You will regret time not spent with a husband, a friend, a child, or a parent." And that's definitely true. I mean, passing the test and doing well in your profession is very important. Doing well in school is very important. But most importantly is God and family. And so I just strongly encourage you to keep that in mind. No matter what, God and family come first. And I really like this joke. What do you receive if you divide the circumference of a jack-o'-lantern by its diameter? And the answer would be ha ha ha, pumpkin pie. So hopefully that kind of lightened the mood just a little bit before we start speaking about measures of variation. Measures of variation, that particular section is a little bit more difficult to describe than the other sections. Before we start, I want to show you this worksheet that's available on Blackboard pertaining to this chapter. And sometimes students say, "Miss Manhart, what's the difference between raw, ungrouped, and grouped?" And so I thought I'd show this to you. Again, raw data, the data values are separated by commas. They could be in a column. So no commas are needed if it's in a column, but there's no particular order. It could be an increasing order or decreasing order or no order, but this is raw. Ungrouped and grouped have a table. If it's ungrouped, you have an X column and a frequency column. If it's grouped, you have a class boundary or a class limit column and a frequency column. So I encourage you to complete this worksheet. And if you notice for the worksheet, I asked you to find the averages. It's completely up to you if you want to do that. It's just going to be extra practice. You may also wish to put these particular values in the calculator. And I forgot to show you the calculator with the last lecture, so I want to show you that now. I showed you how to put in a raw data example, but when you put in an ungrouped data example, and you would go to Stat, and let me just enlarge this so you can see this. Okay, you can see that I need to clear out column L1, and I'm going to use L1 and L2 for ungrouped and grouped. Go to Stat, number 4, and I call up second, and then the button 1. And that's how I call up my list. Done. Then go to Stat and go to Edit. So for this second example, I'm going to do the 10, 11, and the 15. And then my frequencies, 2, 1, and 1. So that's the ungrouped example here on the sheet. 10, 11, 15 would go in the L1 column. 2, 1, and 1 would go in the L2 column. So always put your frequency in the L2 column. So again, make sure everything is correct. And you would go to Stat, Calculate, Enter on one variable statistics. And this is what I do. Some versions of the calculator are a little bit different. I use parentheses and a comma. So let me show you where those are located. You have your parentheses here and the comma. So I'm going to say parentheses, and I'm going to call up my X column, my data column, which is L1. So this is what it looks like. And then I need a comma. Here's my comma. And then I'm going to call up second, and then column L2. And then I'm going to close that in parentheses. So in other words, you have to put your X column first, your data column first, then a comma, and then your frequency column. So L1, comma, L2. Now, the newest edition of the 84 calculator may even be a little bit different from this, where you don't need parentheses. But with my calculator, it's a couple of years old, I do have to have parentheses and a comma. So press enter. And you have your sample mean. And in just a few moments, when we calculate standard deviation by hand, I'll show you how S sub x represents the standard deviation. If you scroll down, you have the median, etc., etc. So going back to stat under edit, you need a L1, L2 column. Now, with group data, the only difference is you would need to find your class midpoints. And the midpoints are very easy. The midpoint between 0 and 2 is 1. Again, if you average the 0 and the 2, you'd have 1. The midpoint between 2 and 4 is 3, 4 and 6 is 5, and 6 and 8 is 7. So my midpoints go in my L1 column, and my frequencies go in my L2 column. And you would calculate it the very same way. So with group data, your midpoints, you'll need to find that column on your own. I do not give you that column, but find your midpoint column the way that I taught you with the previous lesson. Those midpoints represent x, which is your data, and you don't know x, so it represents x. And you put that in the L1 column and your frequencies in L2. And again, you can calculate your mean and your median, and I'm going to show you how to calculate your standard deviation as well. So, measures of variation. There are several measures of variation. And here are the lecture notes if you took the time to print these off. Range, variance, standard deviation, coefficient of variation, and Chebyshev's theorem. This is a very long section, and I'm going to focus on range, variance, and standard deviation before I ever speak about coefficient of variation and Chebyshev. First of all, with range, variance, and standard deviation, I will show you a raw, an ungrouped, and a group. The definition, all of these variations or measurements describe the spread of data values in a set with respect to the mean of that set. So it's kind of like, where is x with respect to the overall mean x bar of the set? Here is an example of raw data. And to explain the measurements of variation, I take two different raw data sets. And each group has 5 students, and we record their grades. And we want to see which class did better. Oftentimes students say that group 2 did better because I have a grade of 100 in group 2. But that's not necessarily true, so keep that in mind. And so, again, we're going to consider these two separate data sets. Two separate data sets. We will see that both groups have the same class average. However, group 1 is actually going to do better. If you were to average all of their grades in each group by adding up their grades and dividing by 5, you get 79. So here's a graph of each group. I have group 1, and I have, these scales are basically the same. You can see 50, 60, 70, 80, 90, and 100. And the X1, the X2, the X3, X4, and X5 would be the grades in the group. So group 1, the first student had a 60, the second student had a 90, the third student had a 70, the fourth student had an 80, and the fifth student 95. And here's the 79, the class average. Group 2, the first student had an 85, the second student a 75, third student an extreme low grade of 50, the fourth student another 85, and the fifth student 100. You can see by the position of the actual grades with respect to the class average that group 1, the scores of the students are less dispersed from the mean, less varied with respect to the mean. Compared to group 2, we had these extreme cases of 50 and 100, so the scores are more varied. Now, less varied in group 1 means they're more consistent with each other. More varied in group 2 means that they are less consistent with each other. As a teacher, we prefer that our students are less varied and more consistent in terms of grades. So Group 1 did better because they're less varied, therefore they're more consistent with each other, more consistent with the overall average of 79. Whereas Group 2, the students are more varied with respect to the mean, so they're less consistent with each other. So we desire the situation in Group 1. And I wrote that all out here for you to read, but I do want to show you the actual calculations of range, variance, and standard deviation for each group, just so you know that Group 1 did better. Now, samples, again, are very important. A statistic is any measurement taken from a sample. A parameter is any measurement taken from a population. For a sample range is capital R, population range is capital R. Sample variance is S squared, and population variance is the Greek letter sigma squared. And that is another Greek letter sigma. There are two sigmas, a capital and a lowercase, and this is still sigma, okay? And that's a S, not a 5, and this is a sigma, not a 6. So S squared versus sigma squared. Sample standard deviation is just S, and population standard deviation is just sigma. Range is very simple. It's the largest value in a data set minus the smallest value in a data set. So if it's group data, it'd be the largest midpoint minus the smallest midpoint. So for the raw data, though, for these two groups, the 95 minus 60 is 35. The 100 minus 50 is 50. Again, Group 1, their range of 35 is smaller. Therefore, it's less varied with respect to the mean. Variance has a complicated formula when it deals with raw data, and I'll tell you what it means. S squared, the summation of a column called X squared, minus in brackets the summation of the column called X, but then you have to square the summation of the entire column, divided by sample size, and that's all divided by sample size minus 1 there. And this is the formula for raw data. So I'm going to do Group 1, and I'll leave it for you to show Group 2. But Group 1, I need my X column and my X squared column. I have squared every X value. I have the sum of the X column and the sum of the X squared column. So here in the formula, the sum of the X squared column is 32,025. Here in the formula, the sum of my data column is 395. But the formula says to then square that sum, so that's 395 squared. Divided by 5, I have 5 students, my sample size, with their 5 grades, all divided by 4. So 205 is the variance. Now with Group 2, I did the same thing. I used the same formula, and their variance is 342.5. Again, Group 1 has a smaller variance, therefore it's less varied, but their grades are more consistent with each other, so they did better. Now, standard deviation is pretty simple. Standard deviation is the square root of variance. So Group 1 is 14.3 and Group 2 is 18.5. Notice how I rounded to the nearest tenth because our raw data values were whole numbers. So the rounding rule says to go out to one more additional decimal place. So in all 3 cases, range, variance, and standard deviation, Group 1 actually did better. Now ungrouped. With ungrouped data, this is how you'll have to find the variance and standard deviation by hand. Of course, you know how to put the information into the calculator as well. And I'm going to show you the calculator with this particular example. I'll let you put a raw data example into your calculator, but I want to show you the ungrouped. The following table gives the grade distribution for 35 students. So I have 35 pieces of data. Find the range, variance, and standard deviation. So 3 students out of the 35 had zeros, which are F's. 6 of them had D's, which is the number 1. 9 of them had C's. 12 of them had B's, and 5 of them had 4s, which is the letter grade of A. And then my frequency column adds up to 35. Now, to find the variance, I have a new formula because it's ungrouped, and I'll show you that on the next page. But that's why I need a F times X column, and by the way, the grade column is the X column, and I need a F times X squared column. So that's the frequency times data value times data value. So in this case, it would be 3 times 0 times 0, 6 times 1 times 1, 9 times 2 times 2, 12 times 3 times 3, 5 times 4 times 4. You're only squaring the x, the data value. Do not square the frequency. And you'll need the sum of each column. And the reason is the variance formula for ungroup is the sum of a frequency times x squared column minus, in brackets, the sum of the frequency times data column, but then you got to square that entire sum of that column divided by sample size minus 1. And if you do those columns carefully, you will be able to plug in 80 squared divided by 35, and then 230 minus that whole number in brackets divided by 34 is about a 1.4. And the standard deviation, now when I find the standard deviation, I don't take the square root of 1.4, I take the square root of the entire value on the calculator, and it's about a 1.2. The range, I didn't speak about that, but the largest grade is 4, which is an A, minus the smallest grade, which is an F, which is 0. So the range is 4. I want to show you how to put this value in the calculator. And when I say calculator, I mean first I want to show you what this formula would look like. You would actually do, and this is how I tell my students to do this if you're using the formula, the 80 squared divided by, 35, is going to be the number that you see here in brackets, 80 squared divided by 35. And then that is 230 minus that number. Instead of retyping the 182.8571429, I like to do second answer. So second, and then all the way down here at the bottom, ANS. And second answer is the number that is the last number that the calculator calculates, which is the 182.857, so that you don't have to round off the 182.8571429. There's the difference in the numerator. And then you divide by 34, which is the denominator. And so there's your exact variance without rounding. And then I like to take the square root, so second and then your square root button. Instead of retyping the 1.38, I just do second answer, because now under the answer button is the variance of 1.386554622, and it's about a 1.2. And the exact standard deviation is 1.177525054. And when I say exact, I really don't mean exact. This decimal actually keeps going. It's irrational. It doesn't necessarily terminate. So you have to be careful with that. The decimal could keep going there. I just know the calculator rounds it off at a certain spot. Now I want to show you stat and then edit. I'm going to clear out, so stat number 4, parentheses, L1, comma, L2, close in parentheses, done. When you go back to stat, in the L1 column, you'll put in your values of 0, 1, 2, 3, and 4, which are your grades. And then 3 students had Fs, 6 students Ds, 9 students C's, 12 students B's, and 5 students A's. So again, put your X's in L1 and your frequencies in L2. Stat, calculate one variable statistics, parentheses, L1, comma, L2. And your standard deviation, SX, is 1.2. If you notice, you will not see S squared, which is variance. So I'll show you how to find that. If you just want to call up the variance. There's a couple different ways. You could do the 1.17752054 and then square it, and that would give you your variance. Or you could go to this list that's above the stat button, but you have to press second stat to receive it. So second stat receives list. Second stat. By the way, here's another area that you can call up columns. If you don't want to call up your columns down here, you can call up your columns by going to second stat. arrow over to math and scroll down to number 8. Variance, enter of what values? L1, L2, the ungrouped, and there's your variance. And then you can take the square root of that, and there's your standard deviation for that problem. So great. That's the ungrouped example there. Now, group data is a Blackboard problem. It's an entrance exam frequency distribution for 108 college students. You are going to need a midpoint column because we will need a column called F times midpoint squared and a column called F times midpoint. We'll need the sum of each column because you can see that it's in the formula here for variance. And the sheet does look like this. I'm just going to explain how the sheet was created. In a problem like this, you would just be given the frequency column and the class limit or class boundary column. Notice how the class boundaries overlap, and we would need class boundaries to construct a histogram so that the rectangles touch. The class limits do not. The class boundaries are created by subtracting a 0.5 and adding a 0.5 to each lower and each upper. So 90 minus a half is 89.5, 98 plus a half is 98.5, and then you would keep subtracting a half, adding a half to receive your class boundaries. The cumulative frequency, the first 6 students out of the 108 score between 89.5, 98.5, or 90 and 98. And then 6 plus 22 is 28, 28 plus 43 is 71, plus 20 is 99, 99 plus 9 is 108, and there's 108 pieces of data or 108 students here and their entrance exams. We don't know the individual entrance exams. We just know 22 of those students score between 99 and 107 or 98.5 and 107.5. But we don't know X. We do know the midpoint. We could average the 90 and 98, add them up, divide by 2. We could average the 89.5 and the 98.5, add them up, divide by 2. But the value that falls between 90 and 98 is 94, and the value that falls between 89.5 and 98.5 is 94. The class width is 99 minus 90, or 98.5 minus 89.5, and that difference is 9. So you could add 9 each time. 94 plus 9 is 103 plus 9 is 112 plus 9 is 121 plus 9 is 130. Or you could find the midpoint going through the formula 5 different times. That's up to you. And relative frequency, I will not ask you, but it's the frequency of each class divided by the total sample size times 100. So 6 students fall here out of 108. So 6 divided by 108, and if you change that to a percent, that's 6% of your student score between 90 and 98, or 89.5 and 98.5. Here, this 22, which is your next frequency, 22 students fall here. So 22 students out of the 108, if you change that to a percentage, that's 20% of your students. You can see that most of your students fall here, 40%. 43 of your students out of 108 students have grades here. And that's going to be 40% if you change that to a percentage. So you can actually draw the histogram. The class width is 9. It's the difference between any 2 consecutive lower limits or any 2 consecutive upper limits. It doesn't matter if you're working with class limits or class boundaries. If you take 2 consecutive lower limits or 2 consecutive upper limits, the difference is always a positive 9. So that's going to be the width of each rectangle, by the way, in the histogram. I will not ask you to construct a histogram, but I will ask you to interpret a histogram. How many applicants do not need to enroll in the summer program? Remember, those scoring, where is that? Applicants scoring above 107 do not need to enroll. And so how many applicants do not need to enroll? 80 of them actually score above 107 here. So 43, 28, and 9 adds up to 80. What percent of applicants do not need to enroll? You could do the 40%, the 26%, and the 8%, and that'd be 74%. What percent of applicants do have to enroll? That means it's 107 or below, and that's the 6 and 22, or the 6 and 20%, and that's 26%. Notice how the 74% and the 26% has to add up to be 100. So here's your histogram. On the x-axis, I have my boundaries that overlap, and you can see those 89.5 to 98.5. The width of each rectangle is 9, so it better look the same to the eye. On the y-axis would be my frequencies. You can increment that the way that you wish. I went 10, 20, 30, 40, and 50. And then the height of each rectangle would be the frequency of each class. So you can see that this particular class, 108.5, and excuse me, that's 107.5 to 116.5. 40% of my students score here, and that's because I have 43 students scoring here out of the 108. So there's my relative frequency inside the rectangles there. But you have your frequency axis and your class boundary axis. And your class boundaries would be the scores. So the rectangles do touch. And on top of each rectangle, I have the frequency of each class. And in the middle here of each rectangle would be the midpoints of 94, 103, 112, 121, and 130. Basically, if I give you a histogram that looks just like this neat and this detailed, you should be able to come up here and rewrite this class boundary column and this frequency column. Just by knowing the class boundary column and the frequency column, you can construct your cumulative frequency column, your midpoint column, and your relative frequency column. So that's what you're going to have to do on a test, okay? Now, the next page, I actually ask you with this group data to find the mean, the median, the mode, the variance, and standard deviation. The mean is the summation of frequency times midpoint column divided by sample size. The median, we have to have our locator formula, so we're looking for the 54th value or student and the 55th, and finding their scores and averaging those scores together, which we don't know their scores, we just know their midpoints. The modal class is the class that occurs most frequently, or the midpoint that occurs most frequently. And then the variance and the standard deviation. At the very bottom, I would once again have the class limit. I could have also put the class boundary column down here. It doesn't matter. The frequency column, the midpoint column. Here's the frequency times midpoint column, and the sum is 12,204. Here's the frequency times midpoint times midpoint. So that would be 6 times 94 times 94. 22 times 103 times 103. 43 times 112 times 112. To get these very large numbers, and that's 1,387,854. So you can see the mean is the sum of all your midpoints divided by your sample size. That's 113. The median, I'm looking for the 54th and 55th members or students. And those students are both here. This is students 1 through 6, all have a 94. Students 7 through 28 have 103. Student 29, the 29th student through the 71st student, all score 112 because we're using the midpoint. So both the 54th and 55th student or members score 112. And if you average 112, you get 112. The modal class is simple. The highest frequency is 43. So that would be the modal, or the mode is 112, but the modal class, I could say 108 to 116 or 107.5 to 116.5. It really doesn't matter. But the mode is 112. And then the variance and the standard deviation, I believe you could calculate on your own, but the variance is 82.3, and if you take the square root of that exact value, you get 9.07 there. Okay, so make sure you can find those. It's very, very important. On the test, you do have to know the 3 different histograms that they speak about in the textbook. They talk about a symmetrical, a positively skewed or right-tailed, a negatively skewed, left-skewed, or left-tailed. With a symmetrical histogram, the mean, the median, and the mode fall at the center, and they're equal to each other. With a positively skewed, right-skewed, or right-tailed, you can see that most of the data, here's the mean, most of the data falls below the mean or to the left of the mean, leaving very little area in the right tail, and it's named after the region where we had the least amount of values or the smaller tail, and so it's right skewed or right-tailed. With the left skewed or negatively skewed, here's the mean, and you can see that most of the data in the histogram falls above it or to the right of it, which leaves a very little area below it or to the left of it, so it's called left-tailed. So hopefully that'll help you, but make sure you know the description. So I would say that here the mean, median, and mode are equal. Here in relationship to the mean, most of the data falls below it. That makes it have a small right tail. It's right-tailed. Here in relationship to the mean, most of the data falls above it. It makes it have a small left tail, so therefore it's left-tailed there. So know what they look like. That's something you may want to put on your 3x5. This is actually coming from the practice test, and it's not clear unless you actually have this printed, but you would take a histogram and you would have the class boundaries and you'd have the frequencies. From there, just knowing the class boundaries and the frequencies, you should be able to receive the midpoints. If you know the midpoints and the frequencies, you can put it into your calculator. And you can calculate the variance, the standard deviation, the midpoint, etc., etc. And I've attempted to do that down here at the bottom. Remember, the midpoints are going to go in your L1 column and your frequencies are going to go in your L2. But you could also calculate the mean, median, mode, mid-range, variance, standard deviation, all by hand using the formulas if you have the appropriate columns. So this would be another example of group data. So you would need a F times midpoint column and a F times midpoint squared column if you're calculating by hand and you don't have a TI 8384 calculator. So make sure you know how to do that. Coefficient of variation is next in the section. It is standard deviation divided by the mean times 100. It's a very easy calculation to calculate. S would be sample standard deviation divided by X bar sample mean, and it would be a statistic, any measurement taken from a sample. Here we have sigma, which is population standard deviation, divided by mu, which is population mean. And then this coefficient of variation will be a parameter, any measurement taken from a population. It allows us, CVAR, coefficient of variation, to compare the variability of two different data sets whose units are different. For example, the average score on an English exam was 85, that's your X bar, with a standard deviation of 5, so S is 5. The average score on history, English and history are different, was 110, that's your X bar, with a standard deviation S of 8. And we would calculate the coefficient of variation for the English and the history. And you can see here that in the English class it's 59.5, but in the in the history class it's 7.3. The larger coefficient of variation, which is 7.3, says that the history class, the scores are more variable because it has the larger coefficient of variation compared to the scores in the English class. So CVAR allows us to compare the variability of two different data sets whose units are different. We don't even know, it looks like to me the English class, the highest grade is like 100, but in history, if the average is 110, we don't even know the point system in those particular classes. Those are two different classes, and the units, the grading system could be completely different. But just by using the standard deviation and the sample mean, we could calculate the coefficient of variation, and the larger one is going to tell us which one is more variable. And therefore, if history, they're more variable, they're less consistent. So that's not necessarily a good thing to be more variable. It means less consistency. Now, Chebyshev is something that students often have difficulty with. And I'll just basically read what you see here. But Chebyshev was a famous mathematician, and he discovered something that applies to every single data set. I often like to tell my students to make up their very own data set. And if you make up your own data set, you could actually prove that Chebyshev's theorem applies. Chebyshev discovered that the proportion of data values from a data set that fall within k standard deviations of the mean will be at least 1 minus 1 over k squared, where k, which represents number of standard deviations, is strictly greater than 1, So if we talk about 2 standard deviations, k is equal to 2, and we put it into Chebyshev's formula, which I call 1 minus 1 over k squared, we get 75%. So Chebyshev said that within any data set anywhere, he would be able to prove that at least 75% of all the data values in the data set will be within 2 standard deviations of the mean. And what that looks like would be x bar minus 2s, x bar plus 2s. So 75% of all the x's, the actual data values in the data set, would be proven to fall between those two numbers. And those would be two numbers. If you know the sample mean and the sample standard deviation, 2 standard deviations below, 2 standard deviations above, you will prove that 75% of the data values fall between those two numbers. If k is 3 standard deviations and you plug it into Chebyshev's formula, 89% of all the data values in the data set will fall within 3 standard deviations of the mean. And you can actually find these two numbers, 3 below, 3 above. And if k is 4, and by the way, k does not have to be a whole number. It just has to be greater than 1. It represents number of standard deviations above and below the mean. But if you plug 4 into his formula, the percentage is even larger. It's 94%. So 94% of all the data values in the data set are guaranteed to be within 4 standard deviations below and 4 standard deviations above. And there's a picture of this. Here's a visual. So you have a data set, and here's the mean. And then these two numbers, and you'll know these two numbers because you'll have the data set, and you'll know the sample mean and the sample standard deviation. This is 2 below and 2 above. This is 3 below and 3 above, 4 below and 4 above. And 75% of all the x's, data values in the set, fall between these two numbers. 89% of all the data values in the set fall between these two numbers, and you will know those numbers, 3 below, 3 above. And 94% of the data values in the set fall within 4 standard deviations of the mean. So I want to prove this with an actual example. You can see that as k, number of standard deviations from the mean, grows larger, the percentage also grows larger. Take the grades of 6 students in the class, and here they are. Prove that at least 75% of all the scores fall within 2 standard deviations of the mean. So you would take this raw data, and it is raw data, and you would average them together, and you would get 63.3 repeating, or 63.3. Since my grades are whole numbers, round to the nearest 10. You can use your TI-84, and you would see the standard deviations about a 23.0 if you round to the nearest 10. 2 standard deviations below, 2 standard deviations above will give you numbers 17.3 and 109.3. Okay? So those numbers would be here. And the mean of 63.3 would be in the center. So I'm using actual numbers. Then what we would do is we would take the scores, and I put check marks above the scores that actually fall within 2 standard deviations of the mean. So if the number falls between 17.3 and 109.3, that means it's within 2 standard deviations of the mean. 80 does, 61 does, 85 does, 50 does, 79 and 25. All of those values fall between those two numbers, which represent 2 standard deviations from the mean. And so not only is that 75, Chebyshev said at least 75, at least means 75% or more. So that's 100%. So Chebyshev's theorem does hold true because it's 100%. At least 75 of the data values fall within 2 standard deviations of the mean. I will also ask you this type of question. Given a data set, and it may be raw, and they're not in any increasing order, you would find the sample mean because it's raw data and the sample standard deviation. Here, I said that S was 6.11. You may want to just leave that as 6.1. I did not necessarily follow the correct rounding rule. You can see that my raw data values are whole numbers, so if I needed to round, it should be 6.1. But in the example, I'm going to go ahead and follow the notes and go 6.110 for the standard deviation. What if the question says, what percent of the data values above actually fall within 1.15 standard deviations of the mean? First, you'll actually have to find the range, which would be the two values that represent 1.15 standard deviations below and 1.15 standard deviations above. And so using your sample mean that you calculated and your sample standard deviation that you calculated, you would have these two values, and they represent 1.15 standard deviations below and above the mean. And so I would go up and count how many of the values fall within 1.15 standard deviations. I have 10 values total, and you see 8 check marks. So 8 out of 10 is 80%. 80% of all the values fall within 1.15 standard deviations of the mean. I really like this question. I give this type of question a lot on exams, so make sure you know how to do that. And then here's another type of question. Suppose that a given data value set has a mean of 80 and a standard deviation of 10. What percent of data values fall between values of 60 and 100? What you'll do is, there's a 3-step process to this. You'll take your larger value of 100 and subtract the mean and receive a difference of 20. To find the number of standard deviations, you will take the difference of 20 and divide by S, that's not a 5, and the S standard deviation is 10, and so that's 2 standard deviations. Then you take K and plug it into Chebyshev's formula, and you know that if K is 2, it's 75%. So 75% of all the data values in a data set will fall between 60 and 100. Know something very neat about this. We don't even know the data set. We don't know how many values are in the data set. We just know that the average is 80 and the standard deviation is 10. Just knowing the mean and the standard deviation alone, we can find the percentage of values that are guaranteed to fall within 2 standard deviations of the mean, and that's 75%. Just by following these steps here. Very, very good example. Now, the empirical rule is Chebyshev's theorem applied to a very special distribution that's said to be normal or bell-shaped. We will cover the normal, bell-shaped, symmetrical histogram or data set in Chapter 6. Make sure you know with the empirical rule the number of standard deviations versus the percentages. The empirical rule only applies to a symmetrical bell-shaped histogram or data set. Chebyshev's theorem applies to all data sets. So with empirical, and they don't give the name if Chebyshev actually came up with the empirical or not, but there may have been another mathematician that after Chebyshev studied his famous Chebyshev theorem, he came up with the, or she came up with the empirical rule. I don't think they really speak about who discovered that. It may have been Chebyshev, not sure. But it says that within 1 standard deviation of the mean, at least 68% of the data values fall. Within within 2 standard deviations of the mean, 95%, and within 3 standard deviations of the mean, 99.7%. So know the number of standard deviations above and below the mean and the corresponding percentage that's promised there in the empirical rule. And that concludes section 3.2 on measures of variation. And we will actually pick up on section 3.3 on measures of position. And that would be the last section of the chapter. And then you should be ready for your test. I hope that you're working on your Connect math assignments. And I hope that you are working on your practice test, because the day before the test, I'll actually allow you to ask questions on those. So I am going to conclude this session, and I hope that you have a blessed day. And again, the next section will be measures of position, and that section is not bad. So have a blessed day.